Thanks a lot for the invitation to speak at this wonderful workshop. So as was just said, I'm going to talk about the connection, or a connection, between quantum error correction and the black hole interior. In particular, I'm going to talk about a construction where I think quantum error correction has something non-trivial to say about the black hole interior. And I should say that there have been previous ideas connecting, or previous proposals connecting these two ideas, especially by Eric and Herman Verlinde, while the starting points of these two different ideas is different, but I think they point in the same direction. Okay, so let me talk about the class of black holes that I'm going to consider. Consider first the eternal black hole. Now, there was this idea that was proposed by this recent paper of Juan Maldacena and Ioana Curcolo about the statement that if you start with a thermal field double, which is dual to the eternal black hole, and then you act with a projection operator on, let's say, the left CFT. So this is a state on left, right, and then you simply project on the left, producing a pure state of the right. This projection has the dual of dropping an end-of-the-world brane from the left CFT. So what this brane does is that it excises this part of the space-time, and therefore you have a pure black hole with a lot of interior. Now, these states are well defined. You can define them using the Euclidean path integral and so on. I don't have time to discuss all of that. Just one more comment I'm going to say about these black holes is that for different projection operators, you can choose to put the brane at various locations in the bulk. For example, you can put the brane sort of in the center, and then you get a solution which looks like the Z2 orbifold of the eternal black hole. And for different P's, you can put the brane sort of wherever you want. Okay, now the next thing I'm going to say is that there seems to be, this seems to present some tension with subregion duality. So tension with SSD, which is subregion duality. I should also warn you that this is a straw man, which I will take down in a bit. So first of all, so what's the statement? So in subregion duality, if you consider the eternal black hole in the thermal field double state, then you can consider some, let's say, a bulk mode here, little a, and another bulk mode here, little b. By subregion duality, the density matrix of A is contained or reconstructible from the density matrix of L. And the density matrix of B is contained in the density matrix of R. Now, this is supported by the fact that if you were to compute the entanglement entropy of, say, the right CFT, so S of the density matrix of R, you would get a piece which is the area of the black hole horizon. So that's this surface here, plus the first quantum correction, which is the entanglement entropy of the bulk mode B. So this is known. But now, what subregion duality is saying, so after acting with this projection operator, this is a pure state of R. And so what subregion duality would say is that by projecting on a pure state of R, you would necessarily also project on a pure state of B. But we know what a pure state of B is. So if you have A and B entangled, we know if you consider the Hartle-Hawking state in the eternal black hole geometry, the modes A would have to be entangled with the modes B. if you were to break the entanglement between A and B, which is what is suggested here, that would obviously form a firewall. And therefore, so the dual of the right state after acting with the projection operator would be everything except for this region. So it would just be this right wedge. But now, what about what I drew there? So there seems to be some tension. And what I'm going to argue is that this picture is wrong. I already warned you about that. And this is what actually happens. But even given that this is what happens, this places some sort of non-trivial constraints on the dictionary of ADS-CFT. So now let me draw the modes again, A and B. Let me draw them here as well, A and B. So this would say that before acting with a projection operator, we had the sort of complementary recovery that A is mapped to L and B is mapped to R. But after acting with a projection operator, both A and B get mapped to R. So this is some constraint on the dictionary of ADS-CFT that after acting with a projection operator, things get rewired. Okay? And what I'm going to discuss is how if you assume the ADS-CFT is a quantum error correcting code or that it implements a quantum error correcting code, then this property is automatic. All right. So I'm going to talk about a very simple model for quantum error correction, which is the random tensor. Now, everything I'm going to talk about today works not just in 1 + 1 dimensional bulk, and not just for these special random tensors. It's a general statement in any dimension, and with a quantum erasure correcting code. Okay, so what is the random tensor? Just a quick introduction. Yes.
So is this only a pastel in 0 + 1 dimension?
No. This is a.
I mean, more generally, you can only have the element of word brain. You put it go to the bifurcation surface or
No.
You can also have this set, this microstate.
You can construct these states in any number of dimensions. Okay, so let's consider. So here's a random tensor. Has a bunch of legs. Let's call these legs L. These legs H, and this leg A. Provided that the dimension of the set of L is greater than the dimension of H times the dimension of A, these tensors give you an isometry from the Hilbert space of A cross H into some subspace of the Hilbert space of L. And the mapping, or this isometry, is defined by defining a so-called tensor state. So this is a state on this tripartite system, L, A, and H. And it has the following form. Sum ij. So these are random tensors in L. That's where the random comes from. I, A, J, H, where this sum runs over an entire basis of A and J. A and H. And now the encoding, so given a state psi AH, what does it get mapped into on L? Well, it's very simple. You just project psi AH on the tensor state. And you can define this as some state S psi of L. Very good. Now, you can think of this tensor from a bulk perspective as sort of describing the dictionary for a pure state black hole. Okay, I'll just draw it. Is this too small? Okay, it's fine. So this is the exterior of a black hole. This is the left CFT. This is some bulk mode A. And this point here is the horizon. So it's describing a pure state black hole where we're being agnostic about what happens sort of inside the black hole, but we have the horizon degrees of freedom here. Good. But we want to talk about an eternal black hole. So what do we do for an eternal black hole? Well, I can draw it here. It's very simple. All you need to do is consider. Yeah, that's fine.
A and H together are the interior.
That's right. The interior of the bulk. Yeah, yeah. Very good. All right, so let's consider now a tensor network for the eternal black hole. So that's very simple. All you need to do is consider two such tensor networks and contract them along the H indices. Okay, so this is, so the tensor state for this, let's call that TT. It's just equal to sort of the sum over H of two tensors T. Okay, and now this describes the following spacetime. L, R, A, B, and these are H. Okay, this defines now an isometry from HA cross HB into HL cross HR with the property that you have complementary recovery. A is mapped to L, and B is mapped to R. Right? There's an isometry from A to L from the original tensor, and from B to R. So again, you can think of consider the mapping that if you have a state psi AB, it maps again to psi AB projected on TT, and that gives you a state. Let's define it as S psi LR. So this is from the bulk to the boundary, but obviously you can go the other way. You can start from the boundary S psi. Say you start with the state S psi. If you project S psi on the tensor state, LR, this will give you back psi AB. So going from the bulk to boundary, then back to the bulk. Moreover, if you were to compute, so start with the state S psi, this is like the thermal field double state. If you were to compute the entanglement entropy of, let's say, the right density matrix in the state S psi, you will get the logarithm of the dimension of H. That's just the, that just comes from these legs, which is just the area of the black hole, plus the entanglement entropy of the density matrix of B in the state psi. All right, so this reproduces two important properties of ADS-CFT, one which is complementary recovery, A is in L, B is in R, and the Ryuta-Kanagi formula with the first quantum correction. Okay, so this is a good toy model for this setup, and you should think of this code subspace as sort of describing the eternal black hole geometry with a few low energy excitations outside the black hole. Okay, so that's the setup. Now let's act with the projection operator. So first of all, let's start in the bulk. So we have the eternal black hole geometry, and we start with the state psi AB of the bulk quantum fields. You should think of psi AB again as the Hartle-Hawking state of the quantum fields on this geometry. You run this state through the tensor network. This gives you a boundary state, which is S psi, as I've defined it there, of left-right. This is like the thermal field double again. And now let's act with the projection operator. Let's do a measurement on the left CFT. So let's act on this state with P on the left, S psi, left-right. So this is now a product. This is an LR product state. We've broken all of the entanglement between the left and the right. Okay, so now we have this new state. Let's just run the state through the tensor network and ask what bulk state do we get? And what does running it through the tensor network mean? You just take that state and you project it on the tensor. So we need to consider S psi LR okay? And the question is whether we get back the state psi AB. So that's this statement, that we had some state of AB, we acted with a projection operator, and we want to see if under going this, this procedure, the state of AB is maintained. And the question is, what are the conditions on the projection operator such that this is true? Before I tell you the result, there are two ways of thinking about the left-hand side of this equation. One is that it's this product state being projected on the old tensor network, or you can think of it as a new pure R state projected on this new tensor network. And this new tensor network, you should think of it as the following. You start with the original tensor network. Where you have R, A, and B, but you replace the left CFT with the projection operator. Okay? Good. Okay, so now let's go back to this. So what are the conditions that this is true? Turns out that it works for any projection that is not correlated with the tensor. And the intuition is actually clear. So consider just the left-hand side of this tensor. So let me just draw that again. That's like, so we had L, A, and H. So if you recall, this is an isometry from AH into L. So if you consider, for example, some product basis of A and H, that maps to some basis in L. If you project on any state of that basis, that would project on a definite state of A. So all you need to do is project on a random state in that basis. And what that projection will do is that it will entangle A with H and produce an isometry from A to H. But this isometry is going to depend on P, on which projection operator you acted with. And so therefore, so going back to this full tensor network, this means that now you have an isometry from A to H, which depends on P. But now remember, there's an isometry from H to R, and therefore A now maps to R. Just a quick comment about B. B is also, there's also an isometry from B to R, which is the original isometry that we had at the beginning. But now you have, now in this tensor network, you have an isometry from HA cross HB into HR, where the recovery map for B into R does not depend on the projection operator, but the recovery map for A from R does depend on the projection operator. Moreover, this question? No. Yes?
This stating state dependence as the interior of Papadodimas and Raju.
That's right. So this is a way of getting state dependence like Papadodimas and Raju, and also by Eric and Herman Verlinde. But I want to say that this is state dependence with a bit more rules. So one difference between these two proposals is that they start with the CFT and try to find something that looks like a black hole interior, So but it's not clear that you actually found the black hole interior. It could be just a fiction. But in this sort of model, you start with a set of black holes that you know have an interior, and then you ask, how is that interior encoded in the CFD? And then you find that it's in a state-dependent fashion. So it turns out that this condition is not very strict, and so therefore you have an entire basis of P's. There's an entire basis of P's which gets the job done. And therefore, this generates for you a large class of states of R, all of which are dual to pure black holes with interiors, but state-dependent interiors. So that's the main punchline of the talk. I have some more comments to make. If there are any questions?
This might be a silly question. In the original tensor network without the projection,
Yes?
why was it that A mapped to L? I would have thought that if you start with any state of A, that would generically map to both L and R.
Yeah, but A maps to L and B maps to R. That's a consequence of this fact, that if you look at any one of these tensors by themselves, there's an isometry from AH into L. For any H, A continues to map to L. So it doesn't matter what you do to H. Here you've contracted it with another tensor. Don?
You said that when the projection is not correlated with P, that this contraction gives you that psi A. Is that really true, or is it just your state proportion of psi A?
So yes, after you act to the projection, you need to renormalize.
So what's the physical interpretation of that change in the norm?
Well,
I understand that when I happen to have chosen an LR state which is in the image of the isometry going outward, but I can undo it this way. But I'm confused about the physical meaning of applying this isometry backwards on a general LR state because of this normalization.
let's see.
It isn't just the projection has the probability of being false, lowering the norm of the state?
That's right, but I'm assuming that I don't know. I mean, this is sort of the collapse problem in quantum mechanics. I'm assuming that you're always in that branch of the wave function, where this projection returns something.
There's something else you could do, which is you could take the whole basis of projections, like in Lemming's talk, and say that you project onto any of them,
Yeah.
and then the probability of success is 1.
That's right.
And presumably the norm doesn't change, but then we have a mixture.
That's right. And this indeed does work for an entire basis of projectors.
But if you don't know which projector it is, you cannot recover it.
That's right. Because the encoding of A into R depends on P, you need to know which projection in order to apply the appropriate unitary to recover A.
This is like the version of quantum teleportation where you do post-selection onto a state. And if you don't want to post-select, then you have to classically communicate
Yeah.
which projector you ended up.
That's right. Okay, now some comments. Now, you might ask, what about the other brain trajectories? Remember we said that different projectors correspond to different brains in the bulk. So I said that there's a brain that does that, there's a brain that does that, and so on. Does this have an interpretation in this story? The answer is yes. The reason why we didn't see it yet is because in this simple tensor network, there was no sort of bulk locality, or we just considered on a single point in the bulk. But you can consider a tensor network with many tensors. So this is the left, and this is the right. You have A, B, C, D, E, and F. Let's say this is where the horizon is. So now if you act to the projection operator here, which is not tuned to any of these tensors, then the break happens here, and A and so forth, everything gets mapped to R. But if your projection operator is tuned to, let's say, the first tensor, then the break happens here, and A gets projected on, but all of the other legs get mapped to the right, and so on and so forth. You can project sort of on any set of legs that you wanted. It turns out that you can also have brains that do this as well. Yeah. Okay, so this gives this picture a bit more credence.
How does the dimension of the space of P's vary as you go in? If I look at the ones that give me everything versus the ones that don't give me A versus don't give me B?
Well, so okay, I don't have a clear answer to the question, although in order for you to project, say, on AB, you need to do more fine tuning. So clearly, the deeper you go in, the fewer the number of P's.
So most projections would just snip off at the end.
That's right. That's right. Yeah.
So if you count the number of P's that are behind the horizon, do you just get the black hole entropy?
Oh, the number of P's, you mean at the horizon?
Right, at or before them.
That might be right. That might be right.
Then, like, how many of these? Because presumably, at least state your user is a projection.
Mm-hmm.
How many of these correspond to like clear enough wood brain?
Okay.
Like have a geometric meaning.
No, actually, now I'm not sure. I mean, there's an entire. I mean, the number of P's is the number of the dimension of this basis is the dimension of H times the dimension of A. I think so it's more than the black hole horizon, more than the black hole entropy number of P's that can project this guy out. So
No, but he asked about the P's that correspond to that cut the system at the horizon.
that's right. That's right.
When the brain is exactly at the horizon, so in the picture that you were drawing there,
Yeah. That's.
should be the black hole horizon, the black hole entropy number.
So I agree there should be at least that many, but
I don't think there can be more.
okay. Okay, that sounds reasonable. Yes, Douglas.
In the case where the projector is like a random projector, it seems like there would be a simpler tensor network that would be at the horizon, right? Putting a random projector at the horizon.
Mm-hmm.
In that case, in that case, your reconstruction of A and things would work, right? Or not?
That's what it seems like. That's what it seems like. That's an interesting question, which I do want to discuss afterwards. But let me make my final comment, which is what does this have to say about firewalls? Okay, so here we have the state. I erased the wrong board. Doesn't matter. Okay, so we were considering tensor networks of this form. Which prepare states of R. Let's say, so here there's some projection, and here there's some state psi. Let's say we initiate this in some state psi AB. So this prepares some state in R. Now, for the firewall, you want to consider a black hole that evaporates away and becomes maximally entangled with the early radiation. And then you arrive at this monogamy problem where the late mode needs to be entangled with the early radiation for unitarity, but it has to be entangled with the interior partner or with the black hole for no drama or for a smooth horizon. But these are large black holes, so they don't evaporate away. you can imagine allowing the boundary of ADS to leak and to arrive at a situation where your CFT-R is now maximally entangled with some other system, and then obviously you can arrive at the same sort of setup for the firewall argument. And so something that would be interesting to study is to allow R to leak and be entangled with some system E. Now, obviously, I cannot study this question dynamically, but something that I can do is consider a set of pure states of R and E, which I then entangle, and then I ask the question whether there's a monogamy of entanglement problem. And so let me consider first the set of states that I want to entangle. So this tensor network, let me put an I here, prepares the following product state, psi I of R, qi of E. So now the question is, what is the tensor network which prepares for me the entangled state of R and E? Well, that's just the tensor sum of these tensor networks. And that produces for me something like this. I should say that let's imagine that this state of AB is sort of a maximally entangled state of A and B. Therefore, you'll find that this sum of, well, first of all, this sum I goes from 1 to dH times dB. And you'll find that if you were to compute the entanglement entropy of R in this state, so SR, you'll find that it's equal to the logarithm of dH plus the logarithm of dB. Okay? So it seems like we've entangled R with E, and it seems like both B and the horizon degrees of freedom are maximally entangled with this external system E. And so now it seems like you've set up the monogamy problem, that now B clearly cannot be entangled with A. But that's a bit too quick. You can rewrite this tensor network as just a sum I, B. So just reorganize things. Since I should have said that these PIs are orthogonal states, PI, you can write this as some unitary U acting on PI. Now, summing over I, you're just summing over the resolution of the identity, or it's just a resolution of the identity, and therefore, you'll just get, okay, I'll just draw it again. You'll just get back the tensor network for the eternal black hole geometry. And so the reason why there's no contradiction or between this value of the entanglement and A and B being entangled is the fact that A now is reconstructible in E, while in each term of this superposition, both A and B were mapped to R. By simply taking a sum and entangling R with something else, A is now recoverable from E, and B continues to be recoverable from R. And so there is no problem with monogamy of entanglement. And R and E, the amount of entanglement between R and E is this guy, which is the area of the horizon plus the entanglement between A and B. Now we know what this is. It just goes by the name of ER equals EPR. Yes, and just literally just 15 seconds, last comment. there's something tantalizing about this result, which is that I could have started with these pure state black holes and encoded a message inside each one of these black holes in A. So there's some message in A now. And you can ask the question of, well, as the black hole evaporates and gets more and more entangled with the early radiation, how does the information inside the black hole end up in the early radiation? Well, what this is saying is that all you need to do is entangle it with the early radiation, and the information about A now becomes reconstructible in E. I think that maybe there's something here to say about the information paradox. Okay, that's all I had. Thank you.